the Cornell Local Roads Program is a good example of a resource to local government and an asset for you guys to really rely on. And so I'll stop there and I'll let Jeff take over, and he's going to talk about kind of the intersection of stormwater and roadways as it pertains to today's topic. Thank you, Jeff.
All right. We're going to try to make this one work. See if I pop a little bit here and there. Can you hear? All right. All right, so we'll try to, we'll cover a little bit about what's already been talked about. I won't get too in depth on it because I know that Kim has covered that quite well. So what I'd like to do is just kind of move on here and talk about weather patterns. Like we've all noticed, there has been large, intense storms that come across. Pretty heavy winds come along with it, high, intense rainfalls. They last 20 minutes and they're gone. But as they pass through, they drop quite a bit of rainfall as they pass through. Several inches in some cases, sometimes even more. So this is the trend we're actually seeing more lately. This is the NRCS maps. This is actually a 100-year storm map that we've got. You can see up here the different rain rates for different areas. If you'll notice, the mountains have a large impact on how much rainfall comes because they catch those clouds and force that moisture out of the rain. More regionally, up in this area here, you get Tompkins County here, we got about 5.5 inches. 5.5 inches is about the 100-year storm. What they're noticing, they've done some studies. I'm echoing. They've done some studies, and what they've noticed is that the 100-year storm is actually now about the 60-year storm. So the frequency of that 5.5 inches showing up is not 1 in 100 chance, but now it's actually a 1 in 60 chance. So there are increases. They're actually these maps here in particular are actually developed from the late 40s into the early 60s. So they're a little bit outdated. So what they're doing is actually going back and try to get more real time with the computers and the technology we've got. They're actually trying to update these things so they're actually more real time to what they're being applied for. So some of the culverts that we're actually using some of this older data. And as we all know, that the storms are not necessarily what they used to be. So that's just one thing to keep in mind. When we talk about stormwater, when I talk about this in my stormwater class, basically I root it all into the water cycle itself. We get our precipitation, falls from the sky. As it falls from the sky, it lands on the top of the soil. Ideally, it's going to infiltrate into the ground. More ideally, to get it past that water table, percolate into the water table itself. Recharging that groundwater, as Kim had referred to several times, that groundwater is critical as far as many things. Not only drinking water, but it helps replenish streams, helps replenish ponds, helps push a lot of that moisture through, helps clean ponds, helps it move, gives it a supply of water to keep it maintained and maintain their water level itself. That which doesn't soak into the ground itself is surface water, otherwise known as stormwater. The sun comes out, obviously these actions occur other times as well. We get evaporation from the ponds and the streams and the storage, return it back into the atmosphere, and then there's the passage that goes up through process of evapotranspiration or transpiration, where the trees uptake that moisture from the ground through the trees as it utilizes it, and then excess passes through the leaves and back into the atmosphere. Essentially completing that cycle. Once it's back in the atmosphere, it falls back to the ground. Some of the critical things to consider on this when it comes to infiltration or dealing with stormwater is what is that water doing when it hits the ground? Come back to land use. Has a great impact on what's actually going to happen. We talk about some of the vegetation, forested areas. You've got the canopy, you've got trees, you've got a lot of organics on the bottom, you've got a lot of vegetation on the base of the forest that take up that moisture as it falls. It sucks that moisture up, holds it, prevents it from shedding off. There will be obviously some moisture that leaves these areas, But for the most part, a good 90% of that rainfall is absorbed into the ground. So there's very little that actually leaves the site. Once you take that canopy out, you remove a lot of the organics, you get a little bit more coming off that ground. You've changed the landscape, you've changed that land use. As Kim had referred, sorry Kim, as Kim has referred to that as that changes, the sponge changes. Now we get into a little bit of land development. You start to input all those impervious surfaces. The rainfall hits that, collects into the roadways. The impervious surfaces can be the rooftops, sidewalks, road surfaces, overly compacted soils, all act as impervious surfaces. And all that water no longer passes into the soil, but hits the surface and channels off and runs down into the streams and the culverts and the ditches that are out there in the roadways. And then once you get to the big box stores, the big malls where you get these sheets of asphalt, you get a good 90% or greater coming off of those areas when the rainfall falls. There'll be some that'll be uptake, some will get caught in pockets within the pavement itself, some will get caught in catch basin sumps, some will, if it's a hot day, a lot of it will actually evaporate directly into the air till it cools. So there is some dissipation back into the atmosphere or holding from some of these situations, but a good portion of it needs to be channeled somewhere else. Just one of the reasons that there is these great big holding ponds in a lot of these developments that we're seeing as far as box stores. You get the Lowe's or the Home Depots. They've got these huge ponds to take that runoff. The idea is to collect that runoff, allow it to either infiltrate back into the ground or hold it and dissipate it over a longer period of time so it doesn't impact the drainage systems that we've got to deal with. Different types of drainage types. Kim had talked about the funnel, different types. Ideally, if you can have vegetated grass ditches along your roads, that's an ideal case, but that's not always possible. A lot of the neighborhoods in central New York have actually put in these concrete curbs. And that's great for collecting the water off the road, but basically that water off the road basically is collected and channeled into a catch basin, and then from there channeled through the pipelines directly into into streams and that sort of stuff, streams and ponds. One of the disadvantages of this is that these roadways tend to collect a lot of pollutants, a lot of atmospheric pollutants, a lot of petroleum products, rust, metals, different types of things that are falling on these pavements are collected in these channels, directed into the catch basins, and then washed directly into the streams and the ponds that are there, which basically affect the water quality of your atmosphere, affect the water quality of your groundwater, affect the water quality of your lakes and your ponds, and indirectly affects the quality of your recreation ability, whether it's fishing or swimming or boating. So understanding that putting these kind of things can actually be detrimental to your water quality further downstream. Allowing that to just shed off into, say, something like this, where it has a chance to infiltrate in, has a chance to decrease, has a chance to filter out some of the pollutants as it goes. And we get some of these other road ditches along the roads. You can see this one's been eroded somewhat. But you can see that there's still, it's got some undulation, it drops. A lot of the energy is dropped as it flows down slowly. So different types of plumbing we've got in here when it comes to channeling, taking streams and large areas of runoff and collecting them into pipes. Part of the problem here is that you're channeling in that. You're shorting that time of concentration. You're taking that water from where it comes from and sending it directly. It's the same effect that you would have if you're straightening out a stream or a pond, a stream or a river. You're taking it and channeling it directly to where you're sending it. It's not taking that ability of the soil and the earth and the atmosphere to uptake that moisture and try to eliminate it as it goes along. So there are some disadvantages to putting it in a pipe. Obviously, there's disadvantages to doing it. But there are some great disadvantages as well going along with it. And you notice this is actually a corrugated pipe. On low flows, that corrugation will actually serve as interference on some of that flow that goes through there. One of the drawbacks for corrugated pipe in this area is a lot of them are steel pipes covered with galvanization. As gravel and pebbles and stone roll through there, which is inherent, you're going to get that regardless, it starts to chip off that galvanization, You end up with pipes that start to rust, again, creating another problem as you go. The other option is a smooth line pipe. They got the 80SN12 pipe is a popular one. It's a black plastic pipe with a smooth interior. The advantages of that is that you don't get the rot, but the disadvantage is that water actually accelerates much quicker as it goes through there. So there are, again, there's benefits and limitations to all of these different types of drainage structures we use associated with roadways. Some of the problems we encounter when it comes to roadways, we get a lot of excess flow that comes onto the roads, out of the fields, out of neighborhoods, wherever it might be, get onto the roads and cause problems. The high velocity is a real killer as far as most of this goes. The force of that water has the ability to pick up sediment, but also dislodge sediment and take it downstream. Has the ability to remove vegetation and soil. Again, once it is picked up, as that water slows down, it drops it out. You get sedimentation problems. Perpendicular flow, all these I'll talk about here coming up. But perpendicular flow is basically streams and culverts hitting the ditches and the problems they cause. And then the poor culvert condition, as I mentioned, with the galvanized steel pipes. With the excess flow, you get problems like washouts. This is actually a picture in Penn Yan after that storm. Obviously an extreme event, but still these are issues we need to cover and steam that need to be addressed. This is also a picture in Penn Yan. They had taken that drainage and actually put it into culverts. When the rain came, it was more than those culverts could actually handle. So it topped over the inlet structure, the catch basins, as it flowed downhill. As you can see, it just washed out all of that material they had put around it and taken it downstream. This is in Penn Yan as well. Not in the village, obviously. This is the upper part of the area. You can see this is just a small swale. This was originally just a swale that went right down the front yard along one of the main roads. And you can see how certain areas eroded based on how it was flowing, how the swirl and how the interruptions were going. So basically took all that sediment. This is some of the stuff that ended up down in the village itself. Overtopping, typically a case of either the culvert inlet being obstructed or damaged. In this case, debris collected in front of that culvert, causing that flow not to be able to go into it. So it crossed over the road, caused the backside of this culvert to wash out. You can see it kind of took out the pipe, took out several pipes, caused a lot of issues with that, again, creating sedimentation down below. High velocity, again, this is the same section looking back uphill now from where we saw where it had washed out on that culvert. The culvert is underneath here. It just bypassed it and went right around it. Again, some stream damage here. You got the flow, starts to eat away, the erosion on the base of the road kind of fall in. Case right here where you kind of overtops, takes out the culvert. Could have been the case of a rotted bottom of the culvert, helps washing it out. But situations of high velocity, the strength of that water, the force of the water in there has the ability of moving that compacted material, moving that material that's placed around it and supposed to stabilize those culverts, and picks it right up, takes it with it. Sedimentation, after all that stuff's been dislodged and passes downstream, you get clogged culverts, damaged culverts. Your ditches fill up with sediment. So sedimentation is a problem. That's, again, another maintenance issue we got to go back and clean out. Perpendicular flows, I mentioned those. These are streams that come into the roadway itself perpendicularly. In this case, it goes under the road. In these cases, they go into the ditches and then need to take a right turn and take a right turn or a left turn, whichever direction the flow is, but in this case, take a right turn and go down the stream or down the ditches. As it comes out, a lot of times there's erosion around these areas on this outer part. There was over on 206, I believe, heading into Green, they had a big flood going out through there, and the hurricanes came through, washed that culverts right out. A lot of that damage was actually caused by water coming out of the fields, runoff coming out of the fields, hitting the connection between the concrete curbing that they had, the swale that they had in there, and the pavement. When that water hit it at the right point, it blew that pavement out and allowed that water to eat away at the road base and underneath the concrete, taking it all downhill, concrete included. So there's issues. The power of water is incredible. Poor culvert condition, whether it's a rusted out bottom, crushed intake, those are all going to restrict the ability of the long-term life of that culvert. This case here, maybe boulders or sticks came down, beat the front of that culvert out. Maybe they were cleaning it and hit it with the machine. Regardless, the capacity of this culvert is going to be restricted because of that. This is a case where the culvert severely washed out. It rusted right out, causing a gaping hole in the roadway. Ended up having to shut it down, caused a lot of problems. So what can be done? Well, inspections. We could try to reduce the velocity. We could try to reduce the volume. And we could try to protect against it, stabilize the roads itself. Inspections should be done on a regular basis. It's not the easiest, but if you're out there, take a quick look as you're passing through. If there's a problem, take a look, take note. Try to rectify those things. You've got culverts like this. It looks like a nightmare. It might cost a lot of money, but there are other options. You could possibly line that. You could possibly pour concrete through it and line just the base. Other solutions that you could do. Again, here's that crushed pipe. Again, restricting. You'll pick that up during your inspections. They should be done pretty much on a regular basis, annually at the very least, maybe in the spring, possibly in the fall before the winter sets in, and absolutely after any kind of storm event. If you miss your inspections, you can see how effective that can be. Sedimentation on this culvert pipe makes it absolutely useless. Here's a case, this is down in Otsego County, on one of the county roads. I was out there, I do a pavement management summer intern program. I was out there taking pictures of cracks. I need them for pictures for my class to teach students what they're looking at. I got looking going, this is interesting. Well, I took a closer look. That's what was behind it. That's a liability for the county. That's somebody had hit that and anticipated, whether it was intentional or not, they anticipate the guide rail to support them and not allow them to go through. They had hit this, they'd have gone right under it. There'd have been all kinds of lawsuits. It would have been a big problem. So, and then there is a stream right here that follows through. It looks like it was a combination of runoff coming down and washing out behind the blocks that they had there, but also underneath, stream running underneath and taking out the support of those blocks. So the combination of them kind of made them topple. But again, just doing regular inspections after the storms and being able to see what's out there, see if you've got damage, see if you've got problems. Diversion, these are actually examples from Otsego County. Taking that water and trying to divert it off. Obviously, if you're in a rural, urban area, you're going to be limited on what you can do and probably don't want to dump it on somebody's property. Particularly, you don't want to dump your water into somebody's backyard. They'll have a fit. But in this case, it actually went into an area that was well vegetated, very stable. Basically took that flow and just redirected it off the road. Ideally, if you're going to do this, you're going to want to take some sort of level spreader, basically a structure that spreads the water out, allows that water to pass over in a slow, large area, and let it flow and dissipate over that discharged area at a slower speed with less energy. There's another case. This is down in Rockland County. They did the same thing. Again, this water was running right down the shoulder, down the road into the guy's garage on a regular basis. They put this little diversion trench in there, no more problems. It was pretty simple, pretty cost effective. Comes to storage, a great way of reducing some more runoff. The sponges, Kim referred to it as. You get the wetlands, you get ponds, even infiltration basins can serve to reduce some of that runoff that's coming through there. Obviously, when it comes to a municipality, you don't have the luxury of extra space or extra funds to go buy property to make this happen, but it is an option. Dry wells, they work as well. They allow that water to infiltrate in, they capture the water, slow the flow down, reduce the flow going downhill, allow that water infiltrate back into the ground, recharge that groundwater, and reduce the volume as you go. Village of Interlaken had a flooding problem. This is just right up the road here. Obviously the village, you can see the confines of the village here. They had a problem right there. The culvert constantly flooded on larger rainfalls. It flooded, came into this point here, down this little stream here, into this point here, flooded, went right down the state highway, and then flooded into the buildings and the yards of the property, constantly creating a maintenance thing, constantly creating problems. This is the stream, this is the size of the stream that was actually contributing it. So there was pretty visible there was a large volume of water coming here. This is actually after the state had replaced the culvert. But this is where it was, and it went down here. Ideally, it would cross here, and then it would take a left turn and discharge down through this little opening here. That's how it is now, and it works well. However, before that, through many discussions with the state, they kept going and going on and on and on. They couldn't get anything done, so the village took steps on its own. They said, well, what are we dealing with? Here's our problem. Where's the water coming from? There's our water supply. That's where the streams are coming. Collecting through here and channeling all the way down here and into the roadway itself. Normal flow should go right out through there. Take it right through the village slowly and do its natural course, and not through the village. Here's the watershed. You can see there's all a bunch of little streams here, so there's small watersheds that go through there. One of the things to note, there is no ponds, there's nothing in here to actually catch the water and try to slow it down. All these other little watersheds, as you can see, you got one here, you got a little pond here. All these are contributing to the watershed that goes down through. All these little ponds are serving as an attenuation of that excess flow, whatever it may be and how often it may be. So what they ended up, this one here, again, didn't necessarily have one, but it had one further up. It was able to collect the contributing runoff from that area and helped attenuate some of that initial flow from the tributaries upstream. So what their idea was, they looked at both sides of the road and tried to determine what might be the best spot. Because down through here, it got a little steep. It was all private property. They tried to look at their options, what they could do. So what they ended up doing was deciding that maybe we'll try to put a pond in here. They worked with the DEC, the Army Corps, Soil and Water, and through their plans, they decided they put in a pond. And that's exactly what they did. Pond was designed by a consultant, had a holding area, had its spread out area so it allowed it to dissipate, get a larger area in there, a little shallower, allow it to infiltrate into the ground, try to dissipate it. And then they had their berm 100-year for the 100-year flood. When the storms greater than the 100-year flood came, they had an outlet structure that would overflow, a basin that would flow right in. And if it were greater than that could handle, they had an overflow that would bypass. So essentially what it did, what happened was with the construction of this pond, it completely eliminated any kind of excess flow. When the state came in and replaced those culverts, this thing's still on. When the state came in and replaced those culverts, they were so undersized, it was ridiculous. But at this point, the problem is solved. So just putting some sort of storage upstream is another option. Again, they worked with the farmer. The farmer was willing to set aside a section of the land that they had so it was usable. And you've got a permanent easement to the land. They have permanent access to it. They can go in there and clean it. They can go and maintain it. They go mow it. And the farmer has access to it as well. It's fenced in. If he wants to put animals out there, he's welcome to do that. So reducing the volume, that's some of the options as far as reducing the volume. That was me. All right, switch. The other one. All right. So in reducing the velocity, several options as far as that goes. Obviously, the riprap, check dams. Again, the idea is to slow the velocity of that flow coming down through there. It's coming off of the roads, coming off of the side land, to try to. Wow, that's sensitive. Try to slow it down. Vertical drops will help dissipate some of that energy as it goes through. You see, this is a stream that comes out. Maybe it's a stream. I don't know. It was pretty heavy. It was right after it had rained. Actually, it was just enough to let the pavement dry as far as the rain goes. But one of these things, basically, as that flow goes through there and drops down these steps, it loses energy. It doesn't have that force velocity as it moves forward, and reduces the potential of picking up sediment, reduces the potential of causing dislodging larger structures, larger problems, causing things downstream. So the idea is basically step it. This is at a discharge, again, the other side of the mountain from Penn Yan. But this is what they've put in there, too. They've stepped it, slowed it down and dissipate that flow. It spreads out beyond that and allows it to just dissipate and meander back into the stream that it originally was. We get linings as far as ditches that they've done on this ditch. You take a closer look, what they did was they stepped it. So there would be dissipation of the energy as it came through. Still using stone, but not necessarily keeping it smooth limestone, taking it and stepping it, and trying to reduce that velocity. Again, note the vegetation and stuff. Ideally, if you can keep the vegetation around your riprap, regardless of how much you put in, get that established, those roots will hold that sediment, that soil in place. Not only will it look better, but it'll prevent a lot of that erosion from creating and going downhill. Check dams are another practice. Again, a lot of these are going to cost money, but you say, can I afford to do that? The question might be, can you afford not to? As Kim had pointed out, how many times are you going to go back and constantly replace that or repair that? So the idea here is basically to, wow, that's changing. The idea here is try to slow the water down and do what it needs to do. This is an example in the town of Lysander. As you can see, one of the drawbacks here is that it isn't revegetated. The soil is actually kind of poor, as my sister-in-law would call it, or my grandmother. It's sour soil, doesn't grow much. It's got low in nutrients, doesn't allow vegetation to take well to it. But what he's done here is he had this stream, this is actually a discharge coming off of a farmer's field. He had a lot of problems with it, and during heavy rains, it would come down. It would wash over top his ditches. It would cross the road. Sediment would come out of the fields. It would clog the culverts on its way down and wash them out. All the culverts along the road down toward the lake would actually be washed out. At the bottom of the hill, just before the lake, because it was all spread out, all that sediment would build in yards. It's collecting garages. It would cause all kinds of damages. So what he ended up doing was putting these these check dams in. This is actually the first check dam out of the farmer's field. You see that it's actually doing its job. It slowed it down somewhat, but it actually trapped a lot of that sediment coming down there and allows these to continue to work as it goes down. Obviously, all of these need maintenance. You need to go back and clean this out. This is due for maintenance. In a larger case, larger check dams, typically you would do these for larger flows. Again, creating these structures, they can be stone, they can be wood, they could be gabion baskets, they could be concrete. But you can see that the flow as it comes through drops through. The idea is try to hold that. The drops will reduce the energy within the water, slow the velocity of the water down. And in some cases, you just want to try to catch sediment, which this one serves to, buddy's probably familiar with this. But it's a good idea, catching that and catch the sediment, allows you to clean it out, and keeps you from cleaning the culvert on a regular basis. Riprap outlets. The purpose of a riprap outlet is basically to slow the velocity of that water after it's been collected into that pipe. Typically, you'll get a stream, but a drainage ditch that's wide and open, and then you collect it and put it into a small pipe. So when it comes out of here, you still got the same amount of water, but it's moving much quicker. So the idea behind the riprap outlet is to allow that water to hit these restrictions and slow that water down so it actually holds that water back, causes less damage further downstream. Splash pools are another option. If you've got high sediment coming through your culverts, you might want to put in a splash pool. The water goes down, catches in there, catches the sediment, allows the water to continue on. So some different options. Again, mostly the use of riprap, but they're not always. When you go to the stabilize, many methods have been used over the years. They've used these big concrete blocks, use large stones and layer them up, or just armoring your inlets and your outlets to prevent that washout from the backside as well. So protecting your structures as well. You can see there's basically going into this culvert here. They've lined those banks. This was actually damaged during the hurricanes that came through, Irene and Lee. Washed this all out, so they came back and placed stone in there to help protect that and keep the erosion down and keep the stream going consistently. In this case here, they used a little bit of riprap, and they stepped it, again, using the ability of losing that energy as it steps out. This is another not necessarily a common one, but they had a big washout through here, coming out of a farmer's field. They put in some gabion baskets and basically built some riprap there, so as it came out, it lost some energy as it flowed through here, and then just swept through the stone itself. Substantially slower rate than it would have if it was just shooting right directly out of the field. Other methods, you can use them in combination, some riprap, some ready rock stone walls, even gabion baskets here. You can see to prevent, because this is actually quite a bit of steep slope, what they did was they spread out that stream. They've got the stream, the water course, the ditch that they had constructed, they opened it up, and again, keep that spread out. The more spread out it is, the less concentrated it is, the slower it's going to be. So they've got basically 3 sets of gabion baskets stacked against each other, and allows it to flow definitely right down into this other drainage ditch. They're just different methods, and then protecting against that. As that water comes down, a lot of times there's a lot of cross culverts that need to be maintained and kept through. Sediment comes down here, a lot of times as the force of water hits these stones, it'll actually ricochet and allow it to flow through, allowing some of that sediment to pass through as well. If that wasn't there, actually before this is actually on 206 as well. Before that was in there, when the storm came down, it basically took that out and clogged the culvert, took this all out, and then the water went right down through the barns, through the yard, through here. Again, creating problems and damage and costly repairs. Different types of stabilization. Again, ideally, if you could get vegetation to grow, that's the way you want to go. On this here, we've got some heavy-duty mats they've placed out. The benefit of this is you can actually lay them in the ditch you have. The vegetation grows up through them. Even though heavy water will come through, it may break off the tops of the vegetation, but the root system's still there. You don't get erosion, and the plants grow back. Use of fabrics, different types of fabrics. Again, try to stabilize those ditches, prevent any kind of washout going down through there. In this case, they put several check dams as it went down there to try. I think initially it was try to stabilize the fabric, but ideally what you would want to do is staple that stuff down, make sure it stays, make sure it holds, tow it into the soil, install it properly, and vegetation will eventually come up through it, and it becomes a stabilized permanent solution. Other methods. Doesn't have to be something you bought. It could be something you have. Using stones, large stones, slabs of stonework. In this case, they use this is actually in Schoharie. This one here is one of those, somewhere around here in Tompkins County. They had a bunch of head walls at the discharge of the pipe. They had a pretty steep embankment. It was washing out. You can see they built it up here with the stone to try to stabilize the road. And they used these little head walls to allow the water to flow down. We'll talk a little bit about the Penn Yan. Use some examples in Penn Yan and how some of these, the repairs they did actually were utilized. Some of the things we talked about. Obviously, we identified where Penn Yan is. These are some of the blue lines for actually county roads. I went out and met with Dave Hartman, superintendent of highways out there for the county. And we rode around, he pointed out some of the problems, some of the things that he thought were problems. We talked about them, and basically, I went back and took photographs. But essentially, in a map he had given me, this kind of dictates how the storm came through. It was pretty limited, but very intense and very focused. You can see the drainage boundaries. So the different watersheds, this part goes this way. These two contributed, went down to this branch of the Keuka Lake, and this good portion of this part went down into Keuka Lake here till you reach a certain point here. I could have put another boundary here, and that went out to this lake here. But the problem areas in dealing with, these are the different areas that the county actually experienced a lot of problems. Again, these are further up in the watershed. The different types of problems, I changed the color on them so it'd be a little bit easier to identify. These are where the perpendicular flows actually flow through and hit the road perpendicularly, causing washouts, flooding, eroding culverts, or washing the road itself out altogether. The yellow ones here are actually the result of accelerating flow running parallel to the roads, causing washouts and ditches and culverts of driveways and various things. There are a few over here. This is actually a stream that kind of meandered underneath the roadway. They had some problems over there. They had accumulation problems down here. They had not only parallel flows, but they also had perpendicular flows that contributed to the flood in that area as well. This area here, as I mentioned, that meandered stream, I've got a few pictures for that. This is the culvert right here. This is some of the debris they removed from that culvert. Another pile of the debris they removed from that culvert. Again, a lot of these streams come off of private land, so you got to work with, a lot of these problems need to be worked with the homeowners and the landowners to try to control or reduce the impact of some of these storms. But just a shot upstream, you can see as this banks erode, those trees continue to fall in there. The next storm is going to carry them down and fill that culvert again. Just being aware of what's going to happen, having a protocol, knowing what you're going to do, understanding what the problems are going to be, what the effects might be. Again, we can't necessarily prevent these things, but we might be able to reduce them when we get those ridiculous flows that we're getting. Another example, right here, this is pretty much a steep slope that comes off of the hill from about this point and works its way down through there. At the lower, about midway in the slope, there's a combination of multiple culverts coming from different sides. You've got two sides of the road, this is a town road. Two sides of the town road are converging into a larger culvert here, and they're sending it directly across here and then down the hill. You can see the erosion that contributed through here. This was the repair they did. This is actually taken a few days ago. Would have been nice if it were green. It would have looked a whole lot better, but they had basically compacted that, laid it out, filled it in. The idea is, again, to help stabilize it, but also try to slow that velocity down to cause any problems. Looking upstream from this same point, you can see that most of the vegetation has been washed out of here. There's another perpendicular stream coming out into this, the road ditch here. You can see it's all been washed out. Not necessarily as steep as it could have been, but it still did damage. The solution here was, again, go back, adding the riprap, making the ditch, make the ditch wide and flat as possible. You allow the water to spread out. If you concentrate it in a steep ditch, you're going to get a lot of erosion. It's going to be hard to vegetate. You may be able to put check dams in a steep ditch, but eventually over time that soil is eventually going to get saturated and slough into the ditch, and you're going to get a lot of sediment build up there as well. So the wider that you can make the stream, the more resilient it's going to be, the longer it's going to last. And then with the addition of vegetation, that's your key as far as preventing a lot of the erosion that goes down through there. Further up the hill, they had taken a lot of this runoff, they had put it in a pipe. I had shown that earlier, some of the pipes that were included there, but this is a portion of the pipe. You'll notice some of that pipe's actually not even in there. This wasn't too long after the flood came through. Well, they took that pipe out. All those pipes, all that subsurface piping has now been exposed to the surface. You've got these ditches. They were able, where the road came off, and I'll show you in the next picture, they're able to stabilize that flow, slow it down enough to where they didn't have to put any riprap all the way down the hill. This is actually turning around looking directly up the hill. From that same point, you can see, I showed you this year earlier that the pipe was actually under here. Well, what they did was they took it all out and they riprapped it. The steeper the slope, they started out with smaller stones. The steeper the slope it got, the larger the stones they got to slow it down. The larger stones are heavier, are able to resist the flow and the force of the flow as it goes down the hill. But they were able to stabilize the flow to a manageable area to where they could actually get it and just let it discharge down a natural vegetated swale. This is actually heading in to just above the village. Again, I showed you this one here. This would have been an ideal spot for reshaping, but also using the excavation that nature had provided and putting some catch dams in. Maybe using that, putting a string, spreading your check dams across, allowing it to slow down, creating a permanent barrier. What they did was they just basically regraded it out, vegetated it. There's a good potential that this one may actually erode again, similar to what had already occurred. Again, it's not as important for some of them. I guess you run out of money, you got to do what you got to do. And then this is just the case of where the sidewalk washed out again from that high velocity and high volume. And this is just the repair that they've come back. They've reset it, replaced a lot of that infrastructure there. So the question is, how do you improve the resiliency of managing stormwater? There's no magic cure. There's no one thing that'll do it all. Working things in combination are most effective. But ideally, if you can reduce the volume, if you can capture the volume, if you can redirect the volume, reduce the volume that's actually going down those ditches is ideal. As we saw with the village of Interlaken, they put a pond in. It was able to actually catch a lot of that upper tributary runoff and allow it to flow out later at a slower rate, so it didn't impact the village as well as severely. Reduce the velocity, using riprap, using stone, using check dams, allowing that water to fall vertically to lose some of that energy. Stabilizing it, again, some of these lining the ditches, you can combine both vertical drops with the riprap to stabilize the ditch. And vegetation, try to reestablish all that vegetation as you go along. And inspect it, knowing what your problem areas are, knowing where you're, knowing if you've got damaged pipes, knowing if you've got sediment buildup, identifying those areas. Eventually you'll begin to identify areas that are consistently problems, consistently sedimenting up, and being able to maintain them more on a regular basis. And as I mentioned, maintenance is the key for all of these structures. Whenever you disturb the land, you got to maintain it. So the key is just basically maintaining that. You can't stress that enough. Go back, clean out that sediment, make sure those culverts are clean, make sure they perform when the unexpected storms come through. And that will do it. Is there any questions? Yes. The question was basically that there's a steep road, Route 34, as it flows down. And they had a blowout about 6 years ago, or was it 6 years ago? 20 years ago, maybe it was. 20 years ago with about 6 inches of rain. And they filled it with shot rock, large stones. And over the years, smaller materials, sediment, sand from the roads, various things coming down through there has actually filled, as I understand, filled those stones up. What it has done is basically taken that friction effect away, but it hasn't allowed that ditch to actually wash away, as I understand. Now your question is what you can do about that. Well, you don't necessarily want to add more rock because then you're building up your ditch, you're reducing your capacity. You could try to wash that out, get in there with a washing process. Again, whenever you put stone in there, it becomes a problem. So there really isn't a whole lot you can do there. The pore space between the stone is eventually going to fill up with some sort of sedimentation. I was taking pictures the other day, and they had some nice rock that they had placed up there in Penn Yan, and I went back there, and from all the sand and everything that they had put on the road had now been plowed into the ditch, and then basically it had filled all that stone up. So what it has done is basically reduce that impact there. So there's not really a whole lot you can do with that. Maybe when you're putting that rock in, you can create steps and try to allow that to dissipate energy in that respect. But an afterthought, it's just one of those things you don't think about with stone. Yes, sir. Yeah, if you're going to dump, the question was if you're going to divert water from your ditch onto some private property, do you need to get permission? Absolutely. Yeah, you should definitely work with the owner because they may have plans of putting a barn there or something, and if it's going to divert into that soil, into that piece of property, you're not going to want to inundate them. It just passes the problem to someone else. So yeah, definitely work with the homeowners, the landowners, try to get their permission as far as any kind of discharge on that. That's very important if you're going to discharge water onto somebody. You got to work with them. Yeah, what he's saying is basically based on the rules of kinetic energy, as velocity is actually mass time acceleration, and the force is actually mass time velocity squared. So what is happening is that as that water accumulates, you're getting much greater in the volume itself, but you're also getting an increase in the velocity itself. So you combine those two forces, and you're substantially increasing up to 25 times the force capacity of that flow coming down there. You can't necessarily build to that. It would almost be ridiculous as far as trying to prevent that. Those are the cases where these extreme events are almost difficult to deal with. What we try to do is protect against the smaller capacities when we can. You can never compete with the floods like Penn Yan had.